Learning objectives. In this chapter, the user will learn the following in detail: requirement verification, coding standards, walkthrough, formal inspection, design validation and verification, function test, design metrics, correctness proof and its requirement. Coding standards. Good software development organizations require their programmers to adhere to some well-defined and standard style of coding. Most software development organizations formulate their own coding standards that suit them most and require their engineers to follow these standards rigorously. What are coding standards? Coding standards are guidelines for code style and documentation. The dream is that any developer familiar with the guidelines can work on any code that follow them. Standards range from a simple series of statements to involved documents. Examples of coding standards. Please refer the following websites: http://www.swtech.com/java/code standard/ http://www.scriptix.com/doc/style guide. Coding standards. Conventions. Good program design. Naming conventions. Formatting conventions. Documentation. Possibly even licensing. Why do we need coding standards? It makes greater consistency between developers, easier to develop and maintain, saves time and money. Prime directive. Document every time you violate a standard. No standard is perfect for every application, but failure to comply with your standards requires a comment. Good coding style. Names. Use full English descriptors. Use mixed case to make names readable. Use abbreviations sparingly and consistently. Avoid long names. Avoid leading, trailing underscores. Documentation. Prepare the document about the purpose of every variable. Prepare the document why something is done, not just what. Accessors. Use getVar and setVar functions on all class variable unless class is being used as a data structure. Member functions documentation. What and why member function does what it does. Parameters, return value. How function modifies object. Preconditions, postconditions. Concurrency issues, restrictions. Internal documentation. Control structures. Why as well as what the code does. Difficult or complex code. Processing order. 3 rules for coding standard. Find a coding standard that works for a team, not for a single person. Standardize early, that is, the effort to bring your old work into the standard. Encourage a culture where standards are followed. Code review. For a module is carried out after the module is successfully compiled and all the syntax errors have been eliminated. Code reviews are extremely cost-effective strategies for reduction in coding errors and to produce high-quality code. Normally, 2 types of reviews are carried out on the code of a module. These 2 types code review techniques are code inspection and code walkthrough. Code walkthrough. Code walkthrough is an informal code analysis technique. In this technique, after a module has been coded, successfully compiled and all syntax errors eliminated, a few members of the development team are given the code a few days before the walkthrough meeting to read and understand code. Each member selects some test cases and simulates execution of the code by hand, that is, by tracing execution through each statement and function execution. The main objectives of the walkthrough are to discover the algorithmic and logical errors in the code. The members note down their findings to discuss these in a walkthrough meeting where the coder of the module is present. Even though a code walkthrough is an informal analysis technique, several guidelines have been evolved over the years for making this naive but useful analysis technique more effective. Some guidelines are: the team performing code walkthrough should not be either too big or too small. Ideally, it should consist of between 3 to 7 members. Discussion should focus on discovery of errors and not on how to fix the discovered errors. If they are being evaluated in the code walkthrough meeting, managers should not attend the walkthrough meetings. Code inspection. The aim of code inspection is to discover some common types of errors caused due to oversight and improper programming. During code inspection, the code is examined for presence of certain kinds of errors. For instance, consider the classical error of writing a procedure that modifies a formal parameter, while the calling routine calls that procedure with a constant actual parameter. In addition to the commonly made errors, adherence to the coding standards is also checked during code inspection. Good software development companies collect statistics regarding different types of errors commonly committed by their engineers and identify the type of errors most frequently committed. Such a list of commonly committed errors can be used during code inspection to look out for possible errors. Some classical programming errors which can be checked during code inspection: use of uninitialized variables, jumps into loops, non-terminating loops, incompatible assignments, array indices out of bounds, improper storage allocation and deallocation. Mismatches between actual and formal parameter in procedure calls, use of incorrect logical operators or incorrect precedence among operators, improper modification of loop variables, comparison of equally floating point variables, etc. Correctness proof and its requirement. What is formal verification proof correctness? A proof of correctness is a mathematical proof that a computer program, when executed, yields correct results, that is, results fulfilling specific requirements. Before proving a program correct, the theorem to be proved must, of course, be formulated. Hypothesis. Hypothesis of such a correctness theorem is typically a condition that the relevant program variables must satisfy immediately before the program is executed. This condition is called the precondition. Thesis. The thesis of the correctness theorem is typically a condition that the relevant program variables must satisfy immediately after execution of the program. This latter condition is called the post condition. Correctness theorem can be stated as: V is true before execution of the program, S is the condition, P will be true after execution of S, where V is a precondition and P is postcondition. Notation. Such a correctness theorem is usually written as VSP, where VS and P have been explained above. Any externally observable aspect of the program's execution may be covered by the precondition and postcondition. Design metrics. Design metrics are useful in measuring the complexity and goodness of a design. A large number of metrics have been proposed for object-oriented designs. Some of these have been validated experimentally, others are mere proposals or have received little or no validation. Assumption. The effort in developing a class is determined by the number of methods. Hence, the overall complexity of a class can be measured as a function of the complexity of its methods. Proposal. Weighted methods per class, WMC. Let class C have methods M1, M2, Mn. Let Ci denote the complexity of method Mi. How to measure WMC? WMC equals summation of I equals 1 to I equals n into Ci. WMC validation. Most classes tend to have a small number of methods and provide some specific abstraction and operations. WMC metric has a reasonable correlation with fault proneness of a class. Depth of inheritance tree. Depth of a class in a class hierarchy determines potential for reuse. Deeper classes have higher potential for reuse. Inheritance increases coupling. Changing classes becomes harder. Depth of inheritance, DIT, of class C is the length of the shortest path from the root of the inheritance tree to C. In multiple inheritance, DIT is the maximum length of the path from the root to C. DIT evaluation. Most classes tend to be close to the root. Maximum DIT value found to be 10. Most classes have DIT equaling 0. DIT is significant in predicting error proneness of a class. Higher DIT leads to higher error proneness. Number of children, NOC. NOC is the number of immediate subclasses of C. Higher values of NOC suggest reuse of the definitions in the superclass in a large number of subclasses. Higher NOC suggests the extent of influence of a class on other elements of a design. Higher influence demands higher quality of that class. Validation of NOC. Classes generally have a small NOC value. Vast majority have NOC equaling 0. Larger NOC value is associated with lower probability of detecting faults in that class. Coupling between classes, CBC. Class C1 is coupled to class C2 if at least one method of C1 uses a method or an instance variable of C2. Coupling is usually easy to identify, though often pointers may make it difficult. CBC of C equals total number of other classes to which C is coupled. Validation of CBC. Most classes are self-contained and have CBC equaling 0. Interface classes tend to have higher CBC values. CBC is significant in predicting fault proneness of classes. Response for a class, R of C. Response set of class C is the total number of methods that can be invoked when the message is sent to an object of C. R of C of class C is the cardinality of the response set of C. Note that even when CBC equals 1, R of C may be high. This indicates that the volume of interaction is high. Validation of R of C. Most classes tend to invoke a small number of methods, low R of C values. Classes for interface objects tend to have larger R of C values. R of C is very significant in predicting the fault proneness of a class. Design validation and verification. Design validation. The process of ensuring that the final product conforms to user needs and requirements. It represents the final stage in the process of ensuring that new designs are fit for the intended purpose before release of the item or system for use. Design verification. It is referred to as qualification testing. It ensures that the product as designed is the same as the product as intended. Project activities in which design verification is useful. Concept through to detailed design. Specification development. Detailed design through to pre-production. Other production tools that are useful in conjunction with design verification. Requirements management. Configuration management. FMEA. Testing may occur at many points during the design process, from the concept development to post-production. This tool will focus mainly on prototype testing. However, many of the guidelines that will be provided can be applied to all testing. Formal inspection. Software inspections are a disciplined engineering practice for detecting and correcting defects in software. Inspections are more formal process than walkthrough, used to collect metrics or statistics about the software process. What do inspections cover? This is a static analysis technique of software testing. Inspection addresses three major tasks of process management: planning, measurement, and control. What can be inspected? Inspections can be held at various points in development process. Fagan recommended inspections on detailed design, cleanly compiled code, completion of unit test. Inspection metrics. Inspections are used to collect quantitative quality data at defined points in the development process. This can be used to give feedback to the developers, feed forward to future development, and feed into future steps of process. Can also provide data on effectiveness of inspection techniques. Inspection roles. Author, developer of work product. Moderator, an inspector responsible for organizing and reporting on inspection. Reader, an inspector who guides the examination of the product. Recorder, an inspector who enters all the defects found on the defect list. Inspector, member of inspection team, often chosen to represent specific role, designer, tester, technical writer, SQA, etc. Who is involved in inspection? At a minimum, a formal inspection includes designated moderator, author of the work, at least one peer inspector. Steps of inspection: planning, overview, preparation, meeting, rework, follow-up. Planning. Planning begins with entry criteria for inspection. Moderator is usually a peer or technical leader. Selection may be made by developer, but this is generally not an ideal situation. Management is encouraged not to look at individual inspection results. Moderator verifies that product meets entry criteria and schedules future steps. Overview. Presentation to inspectors with any background information needed to properly review software product. Data collected is author preparation time and time spent on presentation. Preparation. Individual activity. Author collects all material required for inspection. Inspectors study the material and complete inspection log. Defects are noted at this step but not collected. Meeting. Meeting is conducted by moderator. Agenda includes introduction, establishing readiness, examining material and recording defects, review defects, determine disposition, debrief. Defect data is collected this time. Rework. Performed by the author in response to defect disposition determined at a meeting. Follow-up. Moderator verifies that corrections are made. Moderator completes inspection management report and defect summary report. Requirement verification, verification and validation. Verification is to check whether the software conforms to specifications. Verification question: do we build the system right? Validation is to check whether the software meets customer expectations. Validation question: do we build the right system? Verification and validation requirements. Requirement verification ensures that each step followed in the process of building the software yields the right products. Checks consistency of the software requirement specification and other software development products against the specification. Verification uses methods like inspections, reviews, walkthroughs, and desk checking, etc. Requirement validation ensures that the software being developed will meet customer needs. Checks the software requirement specification against stakeholder goals and requirements. Validation uses methods like black box functional testing, white box structural testing, etc. Conclusion. In this chapter, we have covered the following in detail: requirement verification, coding standards, walkthrough, formal inspection, design validation and verification, function test, design metrics, correctness proof and its requirement.